Hello students, welcome back. Today we'll discuss reactions of aryl halides or haloaryls. Okay, reactions of aryl halides. Aryl halides basically undergo three types of reactions, and these three types are nucleophilic substitution, electrophilic substitution, and reaction with metals. First of all, we'll discuss nucleophilic substitution. Okay. First of all, we will discuss nucleophilic substitution. You see, compared to alkyl halides, aryl halides are less reactive towards nucleophilic substitution. Okay, aryl halides are less reactive than alkyl halides towards nucleophilic substitution, and this is because of some factors. Say factor number 1. In aryl halides, we have a carbon halogen bond in which the carbon atom is sp2 hybridized. But in alkyl halides, the carbon halogen bond has a carbon atom with sp3 hybridization. Okay. So nature of hybridization of the carbon is different in aryl halide compared with alkyl halide. In aryl halides, the carbon undergoes sp2 hybridization, while in alkyl halides it undergoes sp3 hybridization. We know that in case of sp2 hybridization, there is higher S character. Okay, here S character is 33.33%, but in this case S character is 25%. Again, with increase in S character of hybrid orbital, electronegativity of carbon increases. Okay, so this carbon atom has higher affinity to pull the electron pair towards itself, okay, compared to this carbon. As a result of this bond will be somewhat shorter compared to this bond. Okay, the carbon halogen bond in aryl halide will be shorter in length compared to the carbon halogen bond in alkyl halide. If we examine the bond length CCl in case of aryl halide and in case of alkyl halide, what we see, in case of alkyl halide, this bond length is 177 picometer. Okay, but in this case, in case of aryl halide, it is 169 picometer. So the carbon chlorine bond in aryl halide is shorter in length. As a result, this bond will be stronger compared to this bond, because shorter bond will have higher strength, and a stronger bond is difficult to break. Okay, so we can say the carbon halogen bond in aryl halide is more stable compared to that in alkyl halide. This is the first factor regarding the difference in reactivity of aryl halide and alkyl halide towards nucleophilic substitution. Okay, come to the next factor. In aryl halides, factor number 2. In aryl halides, there will be resonance playing. Okay, consider chlorobenzene. This is chlorobenzene. In this case, we will have resonance or mesomeric effect. Look, this pair of electron may come over here so that there is placement of a double bond in this position. As a result, this double bond will break. Hence, we will have this structure. Carbon is positive, chlorine is positive and this carbon is negative. Then there will be resonance, another resonance structure like this. Okay, this one. This one. Another resonance structure will be possible. That structure is this one. Okay. Finally, we may have this structure. See, we have taken the example of chlorobenzene. In chlorobenzene, we have 5 resonating structures. Among those 5, 3 structures have carbon, chlorine, double bond. Okay. Among the 5 structures, these 3 structures contain carbon, chlorine, double bond. As a result of this, we can say that the carbon halogen bond in aryl halide acquires partial double bond character. Okay. The CX bond in aryl halide acquires partial double bond character. Okay. Due to this partial double bond character, the bond becomes stronger and difficult to break. So this is one of the different reasons why aryl halides are less reactive towards nucleophilic substitution compared to alkyl halides. Then come to factor number 3. The phenyl cation is not stable. Suppose this is an aryl halide. Okay. If we imagine heterolytic cleavage of this bond, what will happen? There will be formation of X minus and this cation. Okay. This cation is called phenyl cation. Phenyl cation is not stabilized because of resonance. But the original compound, this one, it is stabilized by resonance. Resonance can increase the stability. So compared to this species is much less stable. So it is difficult to form. Okay. There is another factor, say factor number 4. Factor number 4. Look. Aromatic compounds have loosely held pi electrons. Okay. Say consider chlorobenzene again. For chlorobenzene, we may draw these 2 structures. What does it mean? Over the molecular plane, there exists loosely held pi electron cloud. Okay, there is loosely held pi electron cloud. As a result of this pi electron cloud, the species becomes electron rich. Okay, aromatic systems are usually electron rich. Being electron rich, it will repel the incoming nucleophile. Okay, which will approach to attack the carbon. This carbon. Okay, so aromatic system being electron rich repels the incoming or attacking nucleophile. So this is another reason. In this way, we have discussed 4 reasons for explaining the lesser extent of reactivity of haloarenes or aryl halides compared to haloalkanes or alkyl halides towards nucleophilic substitution. Okay. However, aryl halides may undergo some nucleophilic substitution under very specific conditions. Okay. However, aryl halides may undergo some nucleophilic substitution under very specific conditions. For example, consider chlorobenzene. This is chlorobenzene. Okay. If you treat chlorobenzene with sodium hydroxide at high temperature like 623 Kelvin and high pressure like 300 atm, okay, followed by acidification. Chlorobenzene is treated with sodium hydroxide at very high temperature 623 Kelvin and very high pressure 300 atm, followed by acidification. In that case, the hydroxyl group will be replaced by OH group. So starting from chlorobenzene, we can produce phenol in this case. Okay? Phenol in this case. Similarly, chlorobenzene may react with CuCl at 523 Kelvin in presence of pyridine catalyst. In presence of pyridine as catalyst. In that case, you will have cyanobenzene. So chlorine is replaced by Cn. Cl minus is replaced by Cn minus. Cl minus means chloride ion is replaced by Cn minus, cyanide ion. This is a nucleophilic substitution. It is achieved by treating chlorobenzene with cuprous cyanide in presence of pyridine catalyst at 523 Kelvin temperature. Okay. The same chlorobenzene may be treated with ammonia in presence of CuO catalyst at 523 Kelvin. Okay, 523 Kelvin and 50 atm pressure. 50 atm pressure. In that case, chloride Cl minus will be replaced by NH2 minus. So chlorobenzene will give us aniline. This is another nucleophilic substitution of chlorobenzene. Okay. We may consider another nucleophilic substitution. Say chlorobenzene, when treated with lithium aluminium hydride, it is a complex metal hydride used as a reducing agent by means of hydride transfer. Okay. In this case, H minus hydride ion will replace Cl minus. So in this case, we will have benzene produced. So what is seen aryl halides are less reactive towards nucleophilic substitution because of different types of factors. We have already discussed these factors. Okay. However, under very specific conditions, aryl halides may undergo some nucleophilic substitutions. By taking the example of chlorobenzene, we have discussed this nucleophilic substitution. Chlorobenzene reacts with sodium hydroxide at 623 Kelvin and 300 atm pressure, followed by acidification, gives us phenol. Okay. Then chlorobenzene is treated with CuCN in presence of pyridine catalyst at 523 Kelvin temperature, will have cyanobenzene or benzonitrile. Chlorobenzene is treated with ammonia in presence of cupric oxide catalyst at 523 Kelvin and 50 atm pressure, will get aniline. Chlorobenzene is treated with lithium aluminium hydride to give benzene. All these are nucleophilic substitution reaction of chlorobenzene. Okay. Now we see presence of electron withdrawing group. Presence of electron withdrawing group increases the reactivity of haloarenes or aryl halides towards nucleophilic substitution. Okay. Let us observe this. This is chlorobenzene. Okay. If Cl minus is to be replaced with OH minus, what is the condition needed? Sodium hydroxide 623 Kelvin, 300 atm, okay, followed by acidification. Because initially there will be ONA here, okay. Sodium phenoxide will be formed initially. That sodium phenoxide will give you phenol upon acidification. Now consider para-nitrochlorobenzene. If we carry out the same reaction, treatment with sodium hydroxide followed by acidification, the reaction will occur at lower temperature. That temperature is 443 Kelvin. Okay. So what is seen? Due to presence of nitro group at para position, this species becomes more reactive than this one. Okay. Because nitro group is an electron withdrawing group. It withdraws electron from the aromatic system. As a result of this, the CCl bond, this bond, becomes more reactive. The greater reactivity of this compound compared to this can be understood from the temperature needed for the two reactions. Since it is less reactive, we need higher temperature. Consider this. Cl, say this one. Now we have two nitro groups at position 2 and 4. Okay. This is 2,4-dinitro-chlorobenzene. In this case, if you carry out the same reaction, what product will have? We'll have this product. We have this product. Now this reaction will be performed at again lower temperature, it is 368 Kelvin. So compared to this is more reactive. Hence, the reaction can be carried out at lower temperature. Again, compared to this is more reactive. Therefore, the reaction can be carried out at again lower temperature. The higher reactivity of this species compared to this is because of attachment of two nitro groups. Okay, in this case there are two nitro groups attached. So there is stronger electron withdrawing effect in this compound compared to this one. Okay. Again, see, if we have this compound 2,4,6-trinitrochlorobenzene. In this case, the reaction can be performed simply by treatment with warm water. Okay, this compound mixed with water, heated, gives you that compound. So in this case, sodium hydroxide is not necessary. But in all these cases, other cases, we need sodium hydroxide and the reaction could be carried out at elevated temperature. Now, attachment of 3 nitro groups in this case makes this species highly reactive towards nucleophilic substitution. Okay, so though nucleophilic substitutions are less common in aryl halides, okay, nucleophilic substitutions are less common in aryl halides because they are less reactive. Yet, we can perform nucleophilic substitutions by using specific reaction conditions. Another point is that attachment of electron withdrawing group like nitro group, cyano group, carbonyl group, okay, carboxylic group, ester group, all these are electron withdrawing groups. Attachment of this type of groups to the aromatic ring makes the aryl halide more reactive towards nucleophilic substitution. Okay. Now come to the second type, electrophilic substitution. Okay, electrophilic substitution. See, this is benzene. Suppose there is a halogen here. Okay, this is halobenzene. Aryl halides are less reactive compared to unsubstituted benzene towards electrophilic substitution. Why so? This is because of the minus I effect of the halogen atom. By virtue of the minus I effect, the halogen atom pulls electrons away from the aromatic system, thereby decreasing the electron density at the aromatic ring. So halogen atom, X atom, is deactivating group. Halogen atom is deactivating group. It means halogen substituted aromatic system is less reactive than unsubstituted aromatic system. Okay, but contrary to other deactivating groups, halogen atom is ortho-para-directing. Remember this point. All other deactivating groups are meta-directing. Okay, but halogen, though it is deactivating, it is ortho-para-directing. Halogen is deactivating because of minus I effect. Because of minus I effect, but it is ortho-para-directing because of mesomeric effect or resonance effect. Okay, so it is more difficult to carry out electrophilic substitution of halobenzene, but somehow if you carry out electrophilic substitution, the incoming electrophile will enter either into ortho or into para position. Okay, let us now discuss some electrophilic substitution of haloarenes. Say chlorination. Consider chlorobenzene. This is chlorobenzene. If you treat chlorobenzene with chlorine in presence of ferric chloride catalyst, then the incoming electrophile is Cl plus chloronium ion. It will attach with either at ortho position or at para position. So in this case we may have a mixture of two compounds formed. This is 1,2-dichlorobenzene, this is 1,4-dichlorobenzene, or this is ortho-dichlorobenzene, this is para-dichlorobenzene. Okay. Next, say nitration. You see another point. Between these two products, ortho-dichlorobenzene and para-dichlorobenzene is the major product. Okay, this is the major product. This one is minor product. What does it mean? In the final product mixture, you will have greater extent of this compound and smaller extent of this compound. Okay. Consider nitration. Say chlorobenzene is subjected to treatment with concentrated nitric acid in presence of concentrated sulfuric acid. Okay. This is called nitrating mixture. A mixture of concentrated nitric acid and concentrated sulfuric acid is called nitrating mixture. It is usually used to carry out nitration. In this case also there will be nitration. The incoming electrophile is nitronium ion NO2 plus. NO2 plus will enter either to ortho position or to para position. Now consider Friedel-Crafts reaction. Friedel-Crafts reaction. Two reactions are there, alkylation and acylation. First we will discuss alkylation. Okay. This is chlorobenzene. It will be treated with an alkyl halide in presence of Lewis acid catalyst AlCl3. As a result, we will get this compound and this compound. Okay. So chlorobenzene reacts with methyl chloride in presence of AlCl3 to produce orthochlorotoluene and parachlorotoluene. This is the major product. Then come to acylation. Consider chlorobenzene again. Treat this with acetyl chloride CH3COCl in presence of AlCl3. In this case, we will get this compound plus this compound. This is orthochloroacetophenone. This is parachloroacetophenone. So in this way, we may have different types of electrophilic substitution reaction of aryl halides. Being aromatic compounds, aryl halides easily undergo electrophilic substitution. However, electrophilic substitution in aryl halides is somewhat more difficult to perform compared to unsubstituted benzene. Why so? This is because of the deactivating group halogen atom. Halogen atom is deactivating because of its minus I effect. But at the same time, halogen atom by virtue of resonance or mesomeric effect is orthopara directing. So incoming electrophile will be oriented either to ortho position or to para position. In this way, on electrophilic substitution, we will always get a mixture of ortho and para disubstituted product, and in all the cases the para disubstituted product is the major product. Okay. Now come to the last type of reaction with metals. So first, number one, reaction with magnesium metal. Magnesium metal. Say chlorobenzene is treated with magnesium in dry tar. What we have? We'll have this phenyl magnesium chloride. Then come to reaction with sodium metal. In this case, we have two types of reaction: Fittig reaction. See, this is chlorobenzene. This is another molecule of chlorobenzene. Two molecules of chlorobenzene will react with two atoms of sodium. As a result, we will get this compound. This is called diphenyl or biphenyl plus twice NaCl. This reaction is called Fittig reaction. Fittig. Similar to Fittig reaction, there is another reaction. It is Wurtz-Fittig reaction. Okay. Here, aryl halide and alkyl halide is treated with sodium metal in dry tar, and as a result of the reaction, we will have alkyl-arene. Okay, this is an aryl halide, this is an alkyl halide. As a result of this reaction, we will have alkyl-arene methyl benzene or toluene plus twice NaCl. So this finishes the reactions of aryl halides. In our later classes, we will discuss some more topics. Okay, thank you for attending the class.